All right, so we're starting Unit 9, our last unit, a really important unit, and I hope one that you'll find really informative because climate change is something that has been talked about in the media, it has been discussed by politicians, it has become global policy and legislation. This is a lot like ozone depletion. What we learned about ozone depletion was that the world came together, they created the Montreal Protocol, and they made a decision together, almost 200 nations, that they would tackle this problem together, and the ozone hole is closing because they knew what caused it, they knew where it came from. We're finding alternative ways to use, or actually using different chemicals, we solve the problem. We're facing kind of the same thing with climate change. We're sort of in the middle of that, right? We've got this problem, and so I kind of titled this slide pack today, How Do We Know? Because I think what I want to do is, yesterday you looked at how infrared radiation works, how it energizes molecules, how that creates heat, and so you kind of learned about that on a molecular basis, because most people don't realize that there are some molecules that absorb infrared radiation, which is heat energy, and some that don't absorb very much. And if it weren't for the greenhouse gases like carbon dioxide, we would basically be a cold rock. But because of these greenhouse gases, they're good. They help hold onto the heat. It bounces off the earth. Most of the energy is reflected off the earth as infrared radiation. Those molecules hold on to some of that and keep us warm. The problem is postulated now that we're putting too much carbon dioxide in the atmosphere, and that's causing this issue with global warming. All right, so I'm just going to start off. So the way I want us to think about this, I know people have lots of differing opinions about it, but I'm just going to talk to you about the perspective of the scientists. Why are they worried? This sort of sums it up. We're going to talk today about how this data was gathered. But going back about 800,000 years, if you look at this graph, we know that the red line is temperature and the blue line is CO2 concentration. And so scientists have been collecting data for decades now, and they are going, okay, there seems to be a correlation. Now, we all know as scientists that correlation does not mean causation, but it's worth looking at. So this is how it started, really, in a lot of ways. Actually, we're going to go back to the 1800s, where scientists were worried about climate change. They called it global warming back then. But this is, to me, sort of sums up this problem that we're having, that we're going up in temperature again, as we have before, but as we're going to see in unprecedented rates. And we've got to remember, too, that some of these peaks back here, we don't necessarily want to live where these temperatures were this high. And so we've got to consider that as well. But that there seems to be this correlation between carbon dioxide and temperature. All right. Now, these are the average temperatures really through the Industrial Revolution, sort of spread out. You've got the global temperature and the Arctic temperatures. Notice that the Arctic temperatures are going up higher. We're going to talk later this week about why the North and South poles are heating up at a much more dramatic rate than the rest of the planet. It's called because of the albedo effect. We'll talk about what that is. But you can see that even though there are fluctuations, what we're seeing basically is a trend. So why do we care about this? I highlighted the first two because the first two are happening now. Melting of continental and polar glaciers and sea ice, and a rise in sea level across coastal communities. We're going to see that in the United States, in Louisiana, Florida, we are actually seeing cities go underwater today. Damage to ecosystems and reduced survival of threatened species, reductions in our food supply, agriculture will shift, where maybe once we could grow food, we won't be able to anymore. And an increased threat to human health from new diseases and changing disease distributions. So I wanted to show you this. So I'm going to move my thing. I found this really interesting. I could get so lost in this climate change. I just love it so much. About it's happening today, and that is all of the wide over real-time sea level rise monitoring that's going on in Louisiana. Now, Louisiana, the southern coast of Louisiana, is a series of deltas and low, shallow wetlands. And there are many parts of this part of Louisiana where people are actually having to move because the water is coming up to where places that it has never been before. They're looking at coast-wide monitoring systems, soil monitoring, hydrology monitoring. And if we look at this interesting thing, you can watch. It's showing over time what is actually happening. So here we are start at 1987, we're at 1995. There's a loss of land in the Delta region. It's going underwater. That is happening right now. This is 1932, and then we go through and you can see what's happening. So this is not necessarily something now that's happening in the future. We're actually seeing some of these problems today, and the Louisiana Delta shows a really interesting example of that. Scientists say that sea level rise is probably one of the most definitive markers of climate change. It's caused by the thermal expansion of water. Remember, when we heat substances up, the molecules move around a lot. And so the oceans are expanding. This sea level rise is not due to the melting of icebergs. Remember, if you put a bunch of ice in a glass of water, because ice is actually less dense than liquid water, it's not going to overflow. So we're not worried about the melting of sea ice. But we've got two other problems: the thermal expansion of water, and then the melting of glaciers, because glaciers is land ice. And so land ice is water that will melt and go into our oceans that wasn't there before. Okay. Now, this was a little lesson was given to me when I went back in 2018. I went to Joshua Tree National Park and actually did climate change research at the park. So the National Park Service is looking at how climate change and the increasing temperature of the earth. So let's kind of define that. Climate change means that the average temperature on the planet is going up. Now, locally, there may be places where it will go down and other places will go up higher than others. But remember, this is a global average. The average temperature of the planet is going up. And Joshua Tree is a desert community, and desert communities are hit really hard by this. And we learned this last semester. So I had lunch with Dr. Patrick Gonzalez, who is the head climatologist at the National Park Service and also a professor at Berkeley. And I said, if you were to start with a lesson about how to talk about climate change with students, what would you say? And he wanted me to tell you this, and I think it's wonderful. When we talk about the earth heating, right, we know the temperature is going up. We have thermometers. That is a measurable fact. So, how is it heated up? There are basically only three ways that the earth can heat up. One is the sun proximity. The earth, as it goes around the sun, will wobble at times. That is caused short warming periods. The tilting of the earth, we talked a little bit about that with seasons, but it can also tilt, causing global warming. And sun flares. These are bursts of energy on the surface of the sun. That energy can be transferred onto the surface of the earth. The problem is, if you look at this bottom top part is our average temperature. The bottom part is the solar irradiance. They can actually measure how much sun irradiation is coming to the earth, and it just hasn't changed in this latter part as our temperature has gone up. So scientists today have discounted the impact of these kinds of wobblings, tilting, sun flares as being an issue in our current state of increasing global temperature. Next, what about geologically? The earth is full of energy. We have magma. We studied that in our geology unit. what about the internal part of the Earth? So sun can either come in or it can come from the center of the Earth. However, it has been calculated that the energy emitted by the Earth in a year was found only enough watts to power one light bulb. This is just not enough to cause the changes we're seeing. The third and only other potential source of warming are changes in what we call our greenhouse gases. Our greenhouse gases are our blanket, right? We learned yesterday that they absorb infrared radiation. I'm going to show you what that looks like in a minute. They absorb heat energy, and that keeps us from being a rock of ice, basically. And that's why other planets like Venus that have tremendous amounts of carbon dioxide in their atmosphere are much hotter than Earth. And so these molecules, if we change them by very small amounts, would be the only other possibility for rising temperatures on the Earth. There just aren't any other ways that this could happen. And considering that the concentration of carbon dioxide just to keep our planet stable has been between 200 and 350 ppm, it's not a lot. So changing that very small amount could have significant changes in our average global temperature. So now, this is the electromagnetic spectrum, right? And we're real familiar with visible light, but all of these are coming from the sun. All of these are coming from the sun. And when this comes in, all of this comes from the sun, we have, hopefully, gamma rays are being shielded, X-rays, ultraviolet, all of this is being shielded by our ozone layer, etc. But the visible light, infrared, microwaves, radio waves, all of this is still in our atmosphere. What happens, however, is that this infrared radiation, I'm going to go ahead a couple slides, I think. I meant to do this, yeah. So as the incoming radiation comes in, right, all of those parts of the electromagnetic spectrum are coming in. We've got some that's just going to bounce right back, and it's going to be reflected back into space, 25% in the atmosphere and 5% in the surface. So what happens is that radiation comes in, it bounces off the surface of the Earth, slows down, and a lot of that that's coming off that reflected energy is infrared energy. And so that takes us back to this part of the spectrum. So we get a lot of infrared energy that can either go back off into outer space, which is what it does on the moon, or it can be absorbed by things in our atmosphere that hold on to that energy. Now, if you look at, this is what's called an infrared spectrum. You can actually take molecules, you can radiate them with infrared radiation, and you can look at how much they absorb. So the length of the peak is how much infrared energy they absorb, and you can see that carbon dioxide and methane, infrared radiation absorbs between 2,000, really around 2,500 to 3,000. In fact, I used to use this form of spectroscopy to determine if I had a carbon double bond oxygen molecule in or functional group in my molecule. I would irradiate a molecule, I would see this ginormous peak, and I go, yep, there it is. And so you can see scientifically and spectroscopically that carbon dioxide and methane, and water too, but we're going to talk about water later and how it's different from these other two, they are absorbing infrared radiation, and that is heat. They absorb it, they're vibrating, they're rotating, and that is heat energy. Right? So under typical Earth conditions, we've got, about 30% of it is reflected, 25% is absorbed, and the remaining 45% is onto the surface. It radiates back into the atmosphere or into outer space. And this is the point right here where these greenhouse gases absorb that energy and make us warm like a blanket. So I'm going to stop here. On the next video, we're going to continue our discussion of what this means.